Hello everyone, am I audible? Is the screen visible and is it moving? Is it moving? Okay, thank you. So let's just wait for 5 minutes for others to join. Let's just begin with the today's session. Yeah, so welcome. Yeah, so welcome everyone to the NPTEL course on Introduction to Polymer Physics. This course is instructed by Professor Amit Kumar, Department of Chemical Engineering, IIT Guwahati. I am Shikha Sharma, Research Scholar in the Department of Chemical Engineering, IIT Guwahati. So I'll be the TA of this course for July 2024 semester. And this is a live interaction session for the week 3, which is on the thermodynamics of polymer solutions and blends and determination of polymer molar mass. So in the last class, we have covered several topics, like we were discussing about the thermodynamics of ideal and polymer solutions, which includes its enthalpy, entropy, Gibbs free energy, and then we discussed about the lattice model and how uh, polymeric solution and the polymer and the solvent is dissolved, and how about the uniform mix, how it will homogeneously mix and uniformly distribute in the lattice. And then we discussed about the Flory-Huggins theory, which is about which includes its Gibbs free energy during the mixing, entropy during the mixing, enthalpy during the mixing, and then about the combinatorial entropy we discussed, and then afterwards we discussed about the interaction parameter, which is the chi, and then we discussed about the chemical potential, which is the main driving force for carrying out the mixing of the polymer solutions. And then we discussed about phase behavior, like we discussed the several terms like theta temperature and the critical solution temperature, the upper critical solution temperature and the lower critical solution temperature. And then we discussed about the miscibility and the Hildebrand equation, which involves the solubility parameter. So these all we have already covered, and in the today's class we will be covering these topics: the phase behavior of polymer solutions and blends, and then the phase behavior of polymer blends and block copolymers, and then the determination of polymer molar mass by osmometry. So in today's session we'll be covering these topics and the concepts related to that. Also we will be solving some of the numerical problems, and if you have any doubt, please feel free to share. So let's begin with the today's problems. Question 1 says, which of the following is a characteristic of a metastable state of polymer blends? Option A, a state where the polymer blend cannot undergo transition to another state under any condition. Option B, a temporary state that is not at equilibrium but can persist for a significant time and shows a local minima of free energy. Option C, a state where the polymer blend has reached thermodynamic equilibrium and shows an absolute minima of free energy. Option D, a state that exists only at absolute zero temperature. So it is asking which is a characteristics of metastable state of the polymer. Characteristics of the metastable state of the polymer blend. So what do you think, which option should be correct? As we have gone through the lectures videos, we have learned about the phase diagram and how what are the different states and what are the different stages in the phase diagram. So based on that, can anybody please tell me the answer? Yes, that's correct. Yeah. So option B is correct, which is a temporary state that is not at equilibrium but can persist for a significant time and shows a local minima of free energy. So what actually is metastable state? So metastable state is this state, we can see in the graph this state. Here it is written metastable state, here and here, which is lying between the binodal and the spinodal lines, right? And in this curve, this is this line which is in that proper continuous dark line is binodal line. So in this binodal line, there is this inside it there is a dotted line which is the spinodal line, right? So the area between this is metastable state. In this, a blend will be in the internal equilibrium state, or it is not in the permanent equilibrium state, rather it's a temporary state where there is a temporary equilibrium will be there, and it cannot like it will be there for some time, but and also it shows local minimum of energy, free energy, but it is not a proper like the stable thermodynamic equilibrium state, and is also the absolute minimum of free energy is in the stable state, not in this state. So option C is incorrect because it is signifying the stable state where the polymer blend is in the thermodynamic equilibrium state and showing an absolute minima, not the like local minima of free energy. So when there is a absolute minima of free energy, that is in the stable state, and the system from like metastable state, it can transfer to the stable state under some specified condition, because it is not a permanent equilibrium state, thermodynamically equilibrium state. So system will try to move on to the stable state, but only in the certain conditions. So this curve we have already seen in the lecture, that the x-axis will is the composition, t is the like y-axis is the temperature, where these phase like this curve is there, and in this curve the this two spinodal, the distance between these two spinodal points, it is the phase separated region. So in this region what happens is the polymer blend will not be in the homogeneous single phase, but it will be in the phase separated form, and outside this curve there is this single phase region. So outside this region is the homogeneous mixture of the blend, right? These points are the critical points at these 2 points, critical points, and also the phase separated region is the unstable region, means here the phases like the like the polymer solution or the polymer blends, they will be separated, they will not be homogeneously mixed, so it is a unstable region. So option B is correct, that the metastable state is a region between between the binodal and the spinodal curves and spinodal lines, and it is a state of the internal equilibrium where there is a local minima of free energy, right? Let's move on to the next question. How a metastable state is converted into a thermodynamically stable state in a polymer blend? Option A, melting; B, nucleation and growth; C, shear thinning; D, increase in pressure; E, rapid cooling. So what do you think, which should be correct? Like a state in a like a polymer blend which is in a in a metastable state, as we have already discussed that it is a not a thermodynamically equilibrium state, so system will try to move on to a more stable state, thermodynamically stable state, system will try to move or convert. So what leads to the which process leads to its transition? Any idea? Yes. So option B is correct, nucleation and growth. So what happens actually is, when system undergoes rapid heating or cooling, it does not get enough time to go in a stable thermodynamically equilibrium state. So it goes into the metastable state, and after that when the system gets sufficient thermal energy, it overcomes the energy barrier and go in a stable state. Or what happens in the metastable state, there will be this nucleation and growth, and in the metastable state, and because of that there will be formation of the crystals, and when the crystals will become of the enough large size, or we can say that the system gets sufficient thermal energy so that it can overcome that energy gap or the energy barrier. So the system will now move from the metastable state to the stable state. So the process which is leading is nucleation and growth. Also, in this unlike the phase separated region, what happens is, if the system, this is the, like the system is in the metastable state where it will nucleate and growth, and this energy barrier it will cross and it comes here in the phase separated region. And if there is any of the fluctuation in the unstable region, then what will happen, the phase separation will be there from the homogeneous solution into two different phases, right? When in the phase separated region, if there will be like tiny of the fluctuation, then the phase will separate out from the homogeneous or the single phase region to the two phase system. So what and also the nucleation and growth, it is leading the process of converting the metastable state into a more thermodynamically stable state. So you understand, right, the reason? Yeah, rapid cooling is actually what it is doing. Rapid cooling and heating is a process which leads to the nucleation and growth, and then further it will be, yeah, it will be the nucleation and the growth is the main process which is leading to formation of the crystals, or when the system gets sufficient energy, the barrier to get into the thermodynamically stable state will overcome. Because of rapid heating and cooling, the system goes in metastable state to get the local minima, and so that the system goes in a temporary equilibrium kind of situation. Yes. Let's move to the next question. Which of the following statements is true about the miscibility gap in a polymer blend? A. The miscibility gap only exists at very low temperatures. B. The polymers are always fully miscible at the critical point of the phase diagram. The miscibility gap is typically surrounded by regions of partial miscibility. Option D, the miscibility gap becomes broader as the temperature decreases. So here is the phase diagram also. So what is the miscibility gap in a polymer blend? And then which statement is correct about it? Any idea? Anyone wants to share his or her views? Yeah. You are thinking correct, that option D is correct. Yeah, because this is the miscibility gap. So when the temperature is the low, then miscibility gap, this gap is the maximum. So the miscibility gap becomes broader as the temperature decreases, right? And here at the near the critical point, the miscibility gap is the lowest, right? This gap is lowest. So here the polymeric blends are more compatible in nature. So miscibility gap is the region where the polymers are immiscible and separated into two distinct phases. It is located between the binodal and spinodal lines. It is influenced by temperature, pressure, and the molecular weight of the polymers. As the temperature increases, miscibility gap shrinks, means the compatibility between the polymeric components, it increases. So when the miscibility gap will be lesser, then the polymer compatibility will be higher, and at the higher temperature it happens, right? And opposite of it is miscibility gap is broader at the lower temperatures, which is true option D. Let's move to the next question. The Florey-Huggins, this is a practice problem. The Florey-Huggins interaction parameter for a polymer solvent system is given. So chi, which is the Florey-Huggins interaction parameter, is given as equals to 0.2 plus 125 divided by T is given, right? And the number of the segments per polymeric chain is also given as x equals to 300. Assume the Florey-Huggins equation to apply. We need to calculate four parameters. One is critical composition, which is phi 2c B at T equals to 312.5 Kelvin. We need to calculate volume fraction of the polymer corresponding to spinodal points, and four options are given. Need to see which option is correct. Then see if the spinodal composition is given or the volume fraction of polymer is given at a certain temperature are 0.015 and 0.1796, the value of Florey-Huggins interaction parameter. So we need to calculate here chi s at the same temperature. D, the upper critical temperature is, we have four options and we need to calculate upper critical solution temperature. So let's solve this question. So the Florey-Huggins interaction parameter for a polymer solvent system is given as chi equals to 0.2 plus 125 by T, and x value, which is number of segments per polymeric chain, is given as 300. We need to calculate critical composition. So for calculating critical composition, which is phi 2c, we have this formula 1 upon 1 plus root and square root of x, which is the number of segments per polymeric chain, which is equals to 300. So 1 divided by 1 plus under root 300. So we get the value as 0.0546. So first is we calculated critical composition. Second is for calculating for calculating volume fraction of the polymer corresponding to the spinodal points at 312.5 Kelvin. So let's solve it. So we know the Florey-Huggins interaction parameter for a polymer solvent system, which is chi equals to 0.2 plus 125 divided by T. T we know as given in the question, which is 312.5 Kelvin. So we can just put its value 0.2 plus 125 divided by 312.5, from which we can get 0.2 plus 0.4, which is 0.6. So chi value is 0.6 at 312.5 Kelvin. Now we need to calculate volume fraction of polymers at the spinodal points. So we can apply this formula, which is chi s equals to half multiply by 1 upon 1 minus phi 2, which is the volume fraction of the polymer, plus 1 upon phi 2 x, which is volume fraction of polymer multiplied by the segments. So we have just now calculated chi as 0.6. So we can put 0.6 here equals to half multiply by 1 upon 1 minus phi 2. Phi 2 is unknown, which we need to calculate, plus 1 upon 300, which is the number of the segments of the polymer, multiply by phi 2, which is the volume fraction of the polymer. And from this equation, we are multiplying 0.6 into 2, which is 1.2, equals to, we have taken the like we are calculating this right hand side now as 300 phi 2 plus 1 minus phi 2 divide by 300 phi 2 multiply by 1 minus phi 2, which is equals to 300 minus 1, which is 299 phi 2 plus 1 divided by 300 phi 2 1 minus like 1 minus phi 2. So it can be 300 phi 2 minus 300 phi 2 square. So on simplification, we get this equation, and then further we get this equation, and after solving this equation, we get a quadratic equation, which is 360 phi 2 square minus 61 phi 2 plus 1 equals to 0. So now we need to calculate the roots of this quadratic equation in order to get the volume fraction. So for calculating the spinodal polymer volume fraction, we need to solve this quadratic equation. We need to find the roots. So this equation, how it looks like actually. So it looks like a quadratic equation, which is a x square plus b x plus c equals to 0, right? So here a is 360, b is minus 61, and c is equals to 1. So we can just apply the quadratic formula to find the roots, which is minus b plus minus root b square minus 4ac divided by 2a. So we are just putting the b first, minus b, so minus 61 plus minus under root b, which is b square, which is minus 61 square minus 4ac, minus 4 into a, which is 360, into c, which is 1, divide by 2a, which is 2 into 360. So when we do the square root of 61, we will get 3721, and and minus 4ac, which is 4 into 360, which is 1440, divided by 2 into 360, which is 720, right? So by calculating this, we get two roots as 0.151 and the second is 0.0184. So we get these two volume fraction at the sphenoidal points. So the this is similar to option number second, which is 0.018 and 0.151. So we get this. Now let's move to part C, which is about calculating the sphenoidal, like we have sphenoidal compositions as 0.015 and 0.1796, and we need to calculate the Flory-Huggins interaction parameter at the same temperature. So here the temperature will be taken as 300 because it is saying the same temperature. So we have, like, already in the previous question, what we did was we had already the temperature value. and we calculated the chi, and we had chi value, and then we calculated the volume fraction. But in this question, the formula applying will be same, since we have the volume fractions here, but here we need to calculate the chi value. So let's solve it. The same formula, chi s equals to half multiplied by 1 upon 1 minus phi 2 plus 1 upon phi 2 x, right? So which is equals to half multiplied by 1 upon minus 1 upon 1 minus 0.015 plus 1 upon 0.015 into 300. So x, we already know the number of the segments in a polymeric chain is 300. So, and phi 2, here we have two volume fractions which are 0.0150 and 0.1796. So we are taking this here, the first one 0.015 as phi 2 value, and then we will calculate this and we get the answer as 0.62, which is our interaction parameter or chi value, right? Or we can solve the same question by taking volume fraction of the polymer as 0.1796, which is already given in the question. The same formula we can apply, and we can take the segments of the polymeric chain as 300, and we can calculate uh, this, and we get the same answer 0.61, because uh, like any of the fraction, any of the volume fraction will going to give the same interaction value, same interaction parameter value. So we can approach this question by any of these two methods. Next segment is the upper critical solution temperature we need to find. So we know that the critical temperature equation from the notes, we know that it is Tc equals to B upon 1 plus root x whole square divided by 2x minus में a. This we already know from our lecture notes, and we know that from the question we know that chi is equals to 0.2 plus 125 divided by 2, which is nothing but equals to a plus b by t. So from this we know that a equals to 0.2 and b equals to 125. So we can put in this critical temperature equation b, which is 125 divided by 1 plus x we know already the number of the polymeric segments, which is 300. So under root of 300 whole square divided by 2 into x 300, which is 300 minus a is 0.2. So when we calculate it, we get 348 Kelvin, which is our option number 4th, which is 347.8 Kelvin, right? We can also approach this question in another method. Like first, what we can do is we can calculate the interaction parameter at the critical point, and then we can put into the critical temperature equation, right? So critical um, point, at critical point, what is the chi, which is equals to half plus 1 upon under root x plus 1 by 2x, which is equals to half, which is 0.5 plus 1 upon under root 300 plus 1 upon 2 into 300, which is 0.5594. And now we know the critical temperature equation is equals to B by in terms of chi at C. So B by chi at C minus A, and from the question we know that chi is equals to 0.2 plus 125 divided by T. So which is equals to A plus B by T. So here A we know is equals to 0.2, B 125. So critical temperature equation will be 125 divided by chi at C, which is nothing but 0.5594 minus 0.2, which is A, and we can get 348 Kelvin. So we get the same answer from this approach. 347.8 Kelvin is the correct answer, and we can use either, like we can put directly, we can apply directly the critical temperature equation, or what we can do is we can first calculate chi at critical temperature and then put the critical temperature equation and we can calculate, right? So are you solving the question with me and understanding the question, or you have any other doubt? So let's move to the next question, which is which of the following blends is immiscible? A. SAN PMMA, B. PE PP, C. PC and PS, D. PET and PBT. So which of the following blends is immiscible? Please, can anybody wants to attempt? So let's solve this question, which is saying that option B is immiscible, rest three which are miscible. So on the right hand side there is a table about the miscible blends and the immiscible blends. So SAN and PMMA is given here, that these are, so these are miscible. So SAN PMMA is, this blend is miscible, and this is immiscible, left hand sorry right hand side. So PE, and here it is given PE and PP are immiscible. So option B is for immiscible. This is immiscible, right? And C, PC, PS, these are miscible blends, and then PE, PBT, here it is written PET and PBT, it is miscible. So option B is immiscible. For any polymeric blend to be miscible, there are two conditions. First is a change in the free energy of the mixing, which should be less than 0, or a reaction should be, or anything like the blend, it undergoes a spontaneous reaction. So it should be less than 0. And the second is for being stable, the second derivative of the change in the free energy of mixing with respect to the volume fraction, uh, it should be greater than 0. So these two conditions must satisfy for a blend to be miscible or to be stable. And also sometimes what we do is we use compatibilizers as an additive, so that the two compatible polymers can become compatible and can form a miscible blend, right? So let's move to the next question. Among the options given, choose the most suitable compatibilizer for blending PVDF, which is polyvinylidene fluoride, and acrylonitrile butadiene styrene ABS. Option A, styrene acrylonitrile SAN, B, polybutadiene PB, C, polymethyl methacrylate PMMA, D, nylon. So PVDF, ABS, these are not miscible, and we are using some type of the compatibilizer. Which compatibilizer we should use from these options A, B, C, D, so that these polymers will get miscible. So any idea? So you are saying that nylon 6. Let's see the answer. No, it is answer number C, which is polymethyl methacrylate PMMA. So why? Let's see the reason. So we know the structure of like we know that PVDF, polyvinylidene fluoride, it is made from the its monomer is vinylidene fluoride, not the chloride. So its structure is this, right? We know this, and we know that the ABS is made from the monomeric units will be styrene, butadiene, and acrylonitrile, and it goes under radical polymerization and form the ABS polymer. As the name suggests, acrylonitrile, butadiene, styrene, right? From these it will form. So the option A, which is the styrene acrylonitrile, it is the monomer of ABS. Also the polybutadiene, it is also the monomer of ABS. So these first two, A and B, these are compatible with the ABS but not with the PVDF. That's why they are immiscible, right? So these options cannot be correct. Next is the, we know, like we should find something which is compatible with the PVDF. So PVDF can be immiscible, like can be miscible with the polymers containing the carbonyl group in the side group, but immiscible with the polymeric group which is having the carbonyl group in the main chain. So in the PMMA what happens is it is miscible because of this carbonyl group is in the side chain, not in the main chain. But in the case of the nylon 6 or the polyamide 6, it is in the main chain. So PVDF cannot be miscible with the nylon 6 but with the PMMA. So option C is correct. So you understood why nylon 6 is incorrect, because it is having the carbonyl group in the main chain, but in the PMMA it's in the side chain, so PVDF is miscible with that. So let's move to the next question. The miscibility in binary polymer blends of polyvinyl fluoride and polyacrylate is governed by which one of the following interactions? Dipole-dipole, acid-base type, hydrogen bonding, or ion dipole. So so polyvinyl fluoride and polyacrylate, these two polymers, these are forming the miscible blend, right? But with the help of which type of interaction? So anybody? So you are seeing dipole, right? Let's see the answer. Yes, you are correct. Answer A is correct, which is dipole. What is happening in the structure? We can see in the polyvinyl fluoride there is the F group, right, which is forming this forming the dipole interaction with the O group in the polyacrylate. So these are forming the dipole interaction and forming a miscible blend. So let's move to the next question. Binary polymer blends of polypropylene and polyamide 6 are immiscible from a thermodynamic viewpoint. This is due to, so these two points, sorry, these two polymers, polypropylene and polyamide 6, they are immiscible because they have the low enthalpy of mixing, high entropy of mixing, high enthalpy of mixing, and low entropy of mixing. So anybody wants to attempt this question? So you are saying the high enthalpy of mixing. Let's see which option is correct. So option D is correct, low entropy of mixing. So let's understand the reason why option D is correct. So Gibbs free energy of mixing of a polymeric blend is given by this equation, which is equals to change in the enthalpy of the mixing minus T into multiply temperature into change in the entropy of the mixing. So for a blend to be miscible, its free energy change of mixing should be less than 0 or negative. But here we are seeing that the polymeric blends are immiscible. So free energy uh, change in the free energy of the mixing, it is greater than 0 or it should be positive. So for the left hand side to be positive, this term, overall term, should be greater than 0, right? So for this, delta Hm value should be greater than T delta Sm value, or the delta Sm value should be less than 0, so that minus minus will become the positive sign and the overall it becomes the positive value. But what is happening, we can see that low enthalpy of mixing cannot be correct, because it should have a high enthalpy to like at least greater than T into delta Sm. And then high entropy of mixing is incorrect, because it should be less than 0, so that the overall term can become positive. Now the option C and D we are having, right? But we know that change in the enthalpy of mixing can be positive or negative, but when there is a bond formation or bond dissociation. But in case of the polypropylene and polyamide 6, we have different polarities, and we have the different crystal morphologies. So they cannot mix and they cannot undergo any kind of bond formation and bond dissociation. So immiscible, that means immiscible polymers, they cannot like, since they are having the different polarities and the crystalline morphologies, there is no bond formation and bond dissociation will going to occur. So there will be no change in the enthalpy of mixing. So option C is incorrect. So we are left with option D, which is low entropy of mixing. So option D is correct. So let's move to the next question. A miscible polymer blend is prepared by mixing 10 to the power minus 3 moles of the polymers having the 400 segments per chain with 4 into 10 to the power minus 3 moles of another polymer having 200 segments per chain at 75 degrees Celsius. The Fleury-Huggins polymer-polymer interaction parameter is given by chi equals to 0.1 minus 40 divided by T. Option A is saying the Gibbs free energy change of mixing. From option 4 option we need to calculate, and B is the critical temperature we need to calculate. So the question is saying that a miscible blend is forming, and the polymer A is having 10 to the power minus 3 moles and having 400 chain segments in the chain, and B is having 4 into 10 to the power minus 3 moles and 200 segments in the chain. Temperature is given as 75 degrees Celsius and the Fleury-Huggins interaction parameter is given as 0.1 minus 40 divided by T. And first we need to calculate Gibbs free energy change of mixing, and second is the critical temperature. So let's calculate this question. So for calculating the Gibbs free energy change of mixing, we have this formula, right? So it is equals to RT n multiplied by N1 ln phi 1 plus N2 ln phi 2 plus x1 n1 phi2 into chi. So we know the value of R, we know the value of T. N1 we know that the moles of the polymer 1 is given as 10 to the power minus 3. Phi1 we need to calculate as the volume fraction of the polymer 1. N2 is given as moles of the polymer 2, which is 4 into 10 to the power minus 3 ln. And then phi 2 we need to calculate because volume fraction in the polymer 2 we need to calculate, and x1 we know the segments of the polymer 1 in the polymer 1 chain, which is 400. N1 we know, phi 2 we need to calculate, and chi equation is given as 0.1 minus 40 divided by T. So let's first calculate phi 1 and phi 2. So phi 1 is equals to x1 n1 divided by x1 n1 plus x2 n2. It is the formula, right? The moles, like the volume fraction of the polymer 1 is equals to its segments, which is 400, multiplied by its moles 10 to the power minus 3, and then divide by the total number of the moles. So which is x1 n1 plus x2 n2. So x1 is 400, n1 is 10 to the power minus 3, and then x2 is 200 segments, and n2 is 4 into 10 to the power minus 3. So from the question we just can put in these values in the formula, and we get 1 by 3 as volume fraction of the polymeric chain 1. So for calculating volume fraction of polymeric chain 2, we can just take 1 minus the phi 1, which is 1 by 3. 1 minus 1 by 3 is equals to 2 by 3, right? Also we can calculate the volume fraction of polymer 2 by the main formula, which is x2 n2 divided by x1 n1 plus x2 n2. And we know that x2 is 200, and then n2 is 4 into 10 to the power minus 3, and then divide by x1 n1, which is 400 into 10 to the power minus 3 plus x2 n2, which is x2 is 200 into n2 is 4 into 10 to the power minus 3, and when we calculate we get the 2 by 3. So we get the same value. We know this that x1 phi 1 and phi 2, we know that the volume fraction of the polymeric chain 1 and 2 we calculate with this formula. Now let's calculate the chi value, which is equals to 0.1 minus 40 divided by T. So T in this question is given as 75 degrees Celsius, which we calculate in the Kelvin as 348.15 Kelvin. When we put in the equation, we get the chi value 0.1 minus 40 divided by 348.15, which is nothing but minus 0.0149. And now we have all the values, like we have chi value, we have phi 1, phi 2 value. We can apply the formula of Gibbs free energy change of mixing as this, where R is 8.314, temperature is 75 degrees Celsius or 348.15, multiply by N1. N1 is 10 to the power minus 3 given in the question, into ln phi 1, which we calculated 1 by 3, plus N2, which is 4 into 10 to the power minus 3 given in the question, multiply by ln phi 2, which is 2 by 3 we have calculated, and then x1, which is 400, multiply by n1, which is 10 to the power minus 3, into phi 2, which is 2 by 3, multiply by chi, which is minus 0.0149. So when we calculate it, we get the value as minus 19.375 joule per mole. So, which is a negative. So, this reaction is a thermodynamically spontaneous. Now, the part B is saying to calculate critical temperature. So, what we can do is first calculating the chi parameter at critical temperature value, critical point, and then we can put it into the critical temperature equation. So, chi at C is equal to half multiply by 1 upon root x2, which is the segments in 2, plus 1 upon root x1, which is the segments in 1 whole square, and this will be equals to half. And then this, like we can put x2 as 200 segments and x1 as 400 segments. So the square root of 200 is 14.142, and the square root of 400 is 20, and we can calculate this value and we get 0.007321 as chi at C value, and then we will calculate the chi value, which is 0.1 minus 40 divided by T. This is, from this we get to know about A and B. So A, chi is equals to A plus B by T is there. So we can understand from this that A is 0.1 and B is minus 40. So now we can apply critical temperature equation, which is nothing but critical temperature is equals to B by chi at C minus A, which is B is minus 40 divided by chi at C is 0.07321 minus A, which is 0.1, and now we can calculate temperature at the critical point is 431.593 Kelvin. So have you solved this question and get the same answer? So let's calculate this next question, which is saying that the miscible polymeric blend, which is having phi 2 naught equals to 0.5, is slowly heated to a temperature, and the phase separation will occur into two phases, which are alpha and beta. So the volume fraction of the second polymer in the alpha and beta phases are phi 2 alpha, which is 0.35, and phi 2 beta, which is 0.75, and we need to calculate the volume fraction of the alpha phase. So we can calculate it by the volume fraction of the alpha phase is equals to by this formula, right? So the single miscible phase is converting into the two phase, and we need to calculate the alpha phase volume fraction, which is equals to phi 2 beta, which is the volume fraction of the second polymer in the beta phase, minus phi 2 naught, and then divide by phi 2 beta minus phi 2 alpha phase equals to 0.75 minus 0.5 divided by 0.75 minus 0.35, which is the question in the question given, and we get the volume fraction as 0.625, right? Now let's move to the next question. In the conformationally symmetric A B diblock copolymer showing microphase separation, the sequence of microstructures formed at x into chi equals to 50 with increasing volume fraction of the A block from a small value to a value of 0.5 is, like first option is saying BCC spheres, two HCP cylinders, then high continuous gyroids, and then last is the lamella. See, second option is saying BCC spheres will first form, then bicontinuous gyrates, then HCP cylinders, and last will be the lamella. Option C, third is saying that HCP cylinders will form first, then BCC spheres, and then bicontinuous gyrates, and then last lamella. Fourth is saying HCP cylinders will form first, then bicontinuous gyrates, and then BCC spheres, and last is the lamella. So it is saying that there is a die-block copolymers made from A and B blocks, and it is showing the microphase separation, and it is saying from the volume fraction of A block, which is taken as 0, and then we will increase it till 0.5. So in this order, which are different phases will going to appear. So we have four options. Anybody? Because it is already discussed in the lecture number, like in the second video of this week. Sorry, third video in sorry, second video of this week. The last topic is this only. So anybody wants to attend this? So the option A is correct, which is BCC spheres to HCP cylinders, and then bicontinuous gyrates, and then lamella. So what is happening is, from the volume fraction of 0 till 0.5, which is this, when we go, we get different structures, right? So first, if we see at the 0.5, the lamella will be there, right? And then, which is this curve, the area inside this curve, lamella. And then we will have the HCP cylinders, which is in this region when we go from here to here. Then the bicontinuous gyrates, which is in this area, and last is the like first we will get the lamella here in the inside sphere, and then we'll get the gyrates outside this one. This is the gyrate, and after that we will get HCP cylinders, and last we'll get the BCC spheres. This one, sorry, this one. So from, like, when we decrease, we are seeing in the decreasing concentration, but in the question it is saying from 0 to 0.5, but we have just now seen that from 0.5, which is the lamellar state, and when we decrease the concentration or the volume fraction of the A block, then we will get lamella, then little bit concentration will be low, then gyrates, then HCP cylinders, and when we move towards the 0, we will get the BCC spheres structure, right? And outside will be the disordered structures. Here outside is the disorder. So what is happening at the lamella? There is the complete micro phase separated system will get, like we'll get the A polymer, and then B polymer layer, and then A polymer layer again, then B polymer layer. So we are getting a, when we see at the micro state, or the, then we'll from the help of the transmission electron microscopy and the small angle X-ray scattering, when we see the micro, at the micro level, when we see, then we can see that there is a phase separated, like the one layer is there, then second layer is of the another polymer, then again there is a layer of the first polymer. So these phases are completely, like they are in the separated form at the, when we see at the micro level. But when we go towards the like when we go towards the zero concentration of the volume fraction of the A block, or when we go towards 1, the reason outside this, curve is the disordered state, where what is happening at the both at the microscopic level and the macroscopic level, the phase is the homogeneous, or it is completely miscible, or in the blended form, or in the single phase system. But when we go towards this in the curve, then what is happening, we are getting different microphase separated systems, and we are getting the different concentrations of A and B polymer. So when we see that the volume fraction of the A block is low, which is near, like here in this outside the outermost curve, the like we see the Fa value is here low, near 0 or 1, 0 or zero point 0.1. Then what is happening is the A block polymer, it will be in the sphere form inside a homogeneous homogeneous uh, uh, spreading of the, or the inside a continuous phase of the B block polymer. So B block polymer will be in the continuous system, and A block will be the in the discontinuous form, as in the form of the spheres, right? We can see in this red is marking the A polymer, and blue is in the B polymer. So B is in the continuous form phase, while A is in the spheres form. When we increase the concentration or the volume fraction of A, we get the hexagonal cylinders, HCP cylinders we get. So in this, the spheres will convert into the cylinders of polymer A, and then we get the, when we further increase the volume fraction of A, we get the gyrates, in which the concentration or the volume fraction of A block is further increased. And for, when we reach the um, when we reach the A block and B block in 0.5, each 0.5 proportion, then we get the lamella or the lamellar structure, or in that what is happening is that there is the equal layers of the, layer by layer, the equal proportions of the A and B polymers. Further, if we increase the concentration or the volume fraction of A, we get the gyrates, and again from the, like, it will be in the reverse order, then lamella, gyrates, and HCP cylinders, and BCC spheres. But here what is happening is the, if we see, the red part is more and blue part is less, which is now in the uh, polymer A is in the continuous phase, and the polymer B is in the discontinuous phase, or in the phase of the spheres. So this is happening, and outside is the single phase system is lying. So option 1 is correct, because we are moving from 0 to 0.5 volume fraction of A, and from this we are getting the BCC spheres will convert into the HCP cylinders, and further the bi-continuous gyrates, and last will be the lamella we'll get, which is in the layer by layer um, morphology, or layer by layer micro separated regions we'll get. So next is the osmometry question, in which it is asked, consider a capillary osmometer containing a dilute polymeric solution on one side, and another side is a pure solvent. So what is happening? So we are having this osmometer, capillary osmometer we are having, and one side it is dilute polymer solution, here it is solution, and one side it is just the pure solvent. That's the pure solvent, right? And then it is separated by this semi-permeable layer in between them. The volume fraction of the polymer solution is given as 0.1 and the number of segments per polymeric chain is given as 1000, and the molar volume of the solvent is given as 100 centimeter cube per mole. The osmotic pressure of the solution measured at 300 Kelvin is 300 Pascal. So osmotic pressure is given as 300 Pascal, which is at the temperature 300 Kelvin. Now, assuming Fleury-Huggins theory to apply, we need to calculate the value of the Fleury-Huggins interaction parameter. This value we need to calculate, right? So let's solve this question. Osmotic pressure of the solution is given as 300 Pascal, right? So uh, we know the equation of the osmotic calculation of the osmotic pressure. So which is osmotic pressure equals to RT phi 2, which is the volume fraction of the polymer in the solution. So we know it's given in the question, divide by x, which is the number of the segments per polymeric chain, which is 1000, which is given in the question, and multiply by V1 plus RT, uh, RT we know, and multiply by half minus chi value we need to calculate, and then multiply by phi 2 square, which is volume fraction of the polymer in the solution, then square, divide by V1. So V1, what is V1 bar here? So V1 bar is a polymer solution, uh, like the molar volume, it's molar volume. Since the polymeric solution is very dilute, so what will happen is a molar volume of the solvent will be equals to its solution's molar volume. So the molar volume of the solvent is given as 1000 centimeter cube per mole, which we can put as 10 to the power minus 4 meter cube per mole. So we are uh, taking here, since the solution is very dilute, we can take the molar volume of the solvent equals to the molar volume of the total solution. So we can put V1 bar as 10 to the power minus 4 meter cube per mole. So here we can put 300 as the osmotic pressure, which is given in the question, and then 8.314, which is R into T, which is temperature 300 Kelvin, and then multiply by phi 2, which is the volume fraction of the polymer in the solution, as 0.01, then divide by 1000, which is the segments in the polymeric chain, multiply by 10 to the power minus 4, which we know we have just now taken the molar volume of the solvent is equals to the polymeric solution molar volume, since it is very dilute, plus RT, which is 8.314, multiply by 300, which is a temperature, multiply by half minus chi, multiply by volume fraction of the polymer in the solution, which is 0.01 square, divide by V1, which is 10 to the power minus 4. So when we calculate, we get the chi value. When we solve it, we get the chi value as 0.48. So we get the value as 0.48. So are you following the lecture? Are you getting the same answer, 0.48? Since chi value is less than 0.5, so it is a good solvent, we can say, right? Next question is, which of the following methods is appropriate for measuring number average molar mass of polymer samples having molar mass in the range of 10 to the power 5 to 10 to the power 6 gram per mole? Option A, vapor pressure osmometry; B, end group analysis; C, cryoscopy; D, membrane osmometry. So it is saying that we need to calculate number average molar mass of the polymer sample, and its molar mass is in the range of 10 to the power 5 to 10 to the power 6 gram per mole. So which method out of these will be appropriate to calculate the molar mass? So anybody? So it is in the video number 3 of this week, which is about determination of the polymer molar mass by the help of the osmometry. So which option should be correct? Membrane osmometry? Yeah. True. So membrane osmometry is the method which is used to calculate the number average molar mass and in the range of 10 to the power 5 to 10 to the power 6 gram per mole. Since we know that the vapor pressure osmometry is upper limit is 10 to the power 4 gram per mole and cryoscopy and ebullimetry is 10 to the power 3 gram per mole is the upper limit. So in this 10 to the power 5 to 10 to the power 6 which is a very high molecular weight, only membrane osmometry will going to work, and the cryoscopy cannot work here because it measures its upper limit is very low, and also the vapor pressure osmometry cannot work. Also, we know that vapor pressure osmometry is a complementary to method to the membrane osmometry because it measures at 10 to the power 4, right? While the membrane osmometry measures higher molecular weight, which is 10 to the power 5 to 10 to the power 6. And since the polymer is having higher molecular weight, so the osmotic pressure will be very high, and since the osmotic pressure is high, membrane osmometry will easily going to calculate the higher molecular weight, higher molecular mass compounds. So we can get the mass Mn bar, number average molecular mass, from the membrane osmometry. Next question is, which of the following is a limitation of using osmometry for determining polymer molar mass? So what is its limitation of osmometry? A, it can only be used for very high molar mass polymers. Second, it is less accurate for low molar mass polymers. C, it requires high temperatures for accurate measurements. D, it is only applicable to crystalline polymers. Which option should be correct? We just now discussed in the previous question also. Yes, the option B is correct. Since we know that the like in the osmometry, the main principle is osmotic pressure. So when there is a high number of the polymer solutes which is having high molar mass, then it generates more osmotic pressure and we can get the molar mass value, polymer molar mass value. But in the low molar mass polymers, we get the less accurate values since it will generate low osmotic pressure. Also, we know that this osmometry, in this, the purity of molar mass and the concentration of the polymer is a very important parameter. Also the temperature stability of the osmometer and interference from the electrolytes or any kind of strong interactions or the formation of the aggregate should be avoided to get a more accurate result. It follows the Van 't Hoff equation, which is relating osmotic pressure to the molar mass or to the concentration of the polymers and the temperature, right? So option B is correct because low molar mass polymers, less accurate value will get from osmometry. Next question is the Z average molecular weight can be estimated using and group analysis, osmometry, viscometry or ultracentrifugation method. So what do you think, which should be the correct answer? So the Z average molecular weight can be calculated using ultracentrifugation method because we can see and group analysis is used for Mn value, which is number average molecular weight, and we know osmometry, it is also for Mn value, and then viscometry is for the viscosity average molecular weight. So ultracentrifugation is the correct answer. Also, we can see that the number average molecular weight can be calculated using colligative properties and end group analysis. Weight average molecular weight can be calculated using light scattering method. Viscosity average molecular weight can be calculated using solution viscosity, and Z average molecular weight is calculating using ultracentrifugation, right? So this question says that a solution is containing 1.018 gram of the polymer, which is the protein natural polymer, per 100 gram of the water. This solution is there and is found to have an osmotic pressure is this. So 1.018 gram of the protein, when it is put into 100 grams of the water, it forms a solution which is having the osmotic pressure of 10.5 torr, and the temperature is given as 25 degrees Celsius. So we need to estimate the molecular weight of the protein. So let's solve this question. So it is already given that 1.018 gram of the protein is being put into 100 grams of the water to form a solution. So the osmotic pressure is given as 10.5 torr, right? Which we can calculate into the atmospheric pressure, which is 10.5 torr divided by 760 torr per atm. So for converting the torr, like the osmotic pressure into from the torr to atm, we need to divide it by 760 and we can get 0.0138 atm as the osmotic pressure. Temperature is given as 25 degrees Celsius, which is equals to 298 Kelvin. So we can just calculate, like we can just add 273 in the degree Celsius to convert it into Kelvin, which is 298 Kelvin here in our case. Now we need to calculate the molecular weight of the protein. So for calculating the molecular weight of the protein, with the help of the osmotic pressure, we need to apply this formula of osmotic pressure in a dilute solution, since 1 gram of the protein in 100 gram of the water, so it is a very dilute solution. So we need to apply the formula of a dilute solution. So osmotic pressure is equals to RT. So R is a constant, T is temperature, which is 298 Kelvin, and then NB, which is the number of the moles of solute in the solution, divided by Va naught, which is the molar volume of the pure solvent, and then Na, which is the number of the moles of the solvent in a solution. So Na and Nb are the number of the moles of solvent and the solute in the solution that is in the equilibrium with the pure solvent, which is water, across the membrane, right? And then first, like in this, we need to calculate Na, Nb, and then Va naught. We need to calculate these three because RT are these are already like known. So to first we will calculate the pure solvent molar volume, which is nothing but Va naught, which is equals to molar volume of the water divided by its density at 298 Kelvin and 1 atm pressure, right, which is equals to, so the molar mass of the water is 18, which is H2O, which is 2 into 1 plus 16 into 1. So which is equals to 18 is the molar mass of the water. Then the density of the water is 0.997 gram per centimeter cube, which is already we know that. So by dividing we get the molar mass. So mass, like the molar volume is the mass divided by density. So mass is 18 divided by density 0.997, which is equals to 18.054 centimeter cube per mole. We get the molar volume of the pure solvent. Now we need to calculate the molar number of the moles of the first the solute, sorry, first the solvent, then the solute in the solution. So Na, which is the number of the moles of the solvent, is equals to its molar mass, which is given 100 gram of the water. So 100 divided by the molar, the water, from the formula we know that the given mass upon the molar mass. So given mass is 100 gram of water, then 100 divided by its molar mass, which is 18, and then we divide and we can calculate 5.555 as the moles of the water, right? And now NB we need to calculate. So NB we can calculate from the formula, because of the osmotic pressure, like we know already, the osmotic pressure already we know this value, which is nothing but 0.1382 atm, right? So we know the osmotic pressure, and then we know this osmotic pressure we already know. We know R, we know T, right? NB we need to calculate, and then VA we have just now calculated as 18.054, and then NA we just calculated as 5.555. So we can calculate NB from this equation of osmotic pressure in a dilute solution as NB equals to pi, which is osmotic pressure, multiplied by number of the moles of the solvent multiplied by its molar volume of the solvent divided by R into T. So we can just put these value as 0.01382 multiplied by 5.555 into 18.054. These all we have three values calculated in the previous slide we have seen. Then R is 82.06 centimeter cube atm mole inverse Kelvin inverse, and temperature we know 298 Kelvin, and when we put we get the moles of the polymer in the solution, which is 5.668 into 10 to the power minus 5 moles. Now we calculate molecular weight, which is nothing but mass of the polymer, which is protein, divided by its moles, which is the mass is already given, that the given weight is 1.018 divided by 5.668 into 10 to the power minus 5, which is equals to 17960.5, which is equals to around 18,000 gram per moles of the molecular weight of the protein is calculated. So you understood? Get the same answer? So next is the find the osmotic pressure of a solution of 1 gram of the glucose in 1000 centimeter cube of the water at 1 atm and 25 degree Celsius. So it is, we are like we need to calculate the osmotic pressure in the solution we need to calculate, and the solution is being formed by adding the 1 gram of glucose in 1000 centimeter cube of the water. So let's just calculate. So for calculating the osmotic pressure, we can apply the Bent Hoff equation, which is nothing but osmotic pressure into volume is equal to nRT, which is we can calculate from this. We know the n value, like we can calculate the n value because we know the molar mass and the molecular weight we know, so we can calculate, right? Like so R or T, R and T we know already, like we can put from the question T value, and then V we also know it is given in the question that the volume of the solvent is nothing but 1000 centimeter cube water. So let's just first calculate the number of the moles of the glucose, which is its the weight given, which is 1 gram of the glucose is given, and divide by its molar mass of the glucose, which is 180.16 gram per mole, or we can calculate by the its chemical structure, which is C6H12O6. So 12 into 6 plus 12 into 1 plus 16 into 6. So we get 180. So we can divide the given weight 1 divided by 180, its molar mass, which is giving its moles, which is 0.005551. And now in the Van 't Hoff equation we can calculate the osmotic pressure is equals to the moles of the glucose 0.005551 into R, which is 82.06, multiply by T, which is 25 degrees Celsius or 298 Kelvin, and then divide by its volume of the solution, which is 1000 centimeter cube water. So when we calculate it, we get 0.1357 atm as the atmospheric pressure. And when we want to convert it into the torr, how we can convert? We can just multiply this into 760. When we multiply this by 760, we get 103.132 torr, right? So in the figure in the right hand side, we can see that this is a setup of how a osmometer looks like. So on the right hand side, we have the pure solvent, which is water. In the part B side, in the part on the left hand side, we have the solution, which is glucose in water, and it is separated by a semi-permeable membrane, and then the osmotic pressure will apply, and then there is a movement of the solvent towards the solution, right? And then there will be this generation of the osmotic head, right? So we get the osmotic pressure as 103.132 torr here. We can also calculate that what is the height, like when there is a pure solvent, how like the solvent height will be there in the left side, how much the height the solution will lift in the left tube. So height in the left tube is equals to 103.132 torr divided by 10, which is 10.3132 centimeter into the density, like into 13.6, which is density of water is 1 by 13.6 times of the mercury. So we are computing like the height, uh, like we know that the mercury is very like it's very dense, so the density of water is it's 1 upon 13.6 times. So for calculating the height, we just multiply the rho, which is the density, multiply by the pressure we are getting, right? So 10.3132, so we get the value as 140.3 centimeter. As we know, the formula is pi is equals to rho gh, right? So we have take from pi equals to rho gh, what we are calculating h, which is the height, right? So we can write pi equals to, we calculated already the osmotic pressure, right? Now we know, we need to understand how height is being calculated, right? So pi is equal to rho gh. So h we need to calculate, rho we know, sorry, the pi we know 103.132 g, we can divide pi by rho g, we can get height, right? So rho is density of the what density, and g is the 10, which is the gravitational acceleration. So we divided this osmotic pressure divide by 10, so we got 10.3132, and then we divide it by uh, rho is 1 upon 13.6, so we multiplied by 13.6 and we get the height as 140.3 centimeter as the height in the this left tube. So ठीक है, so you understood, right, how we calculated this. So this large value of osmotic pressure is required to increase the chemical potential of A, which is the A in the solution, to that of the pure A, which is A is water here. Since the chemical potential of a component of a condensed phase is rather insensitive to pressure. So we instead, like in the pure solvent, we need not to have that much of osmotic pressure as compared to the solvent and the solute system. So have you get the same answer? Okay, so let's move to the next question, which is the osmotic pressure data for polystyrene of molecular weight. So we have polystyrene, which is having molecular weight of 1.6 into 10 to the power 6, and the equation is given as A2, which is second viral coefficient equation is given. So the osmotic pressure data for polystyrene of a molecular weight ये yielded according to this equation, and the following values for the second viral coefficient: A 2.88 10 to the power minus 4 mole centimeter cube per gram square in dichloroethane, and second is the minus 0.37 into 10 to the power minus 4 mole centimeter cube per gram square in cyclohexane. Both at 22 degree Celsius. So we need to determine chi, which is, we need to determine Fleury-Huggins interaction parameter in this polymer solvent system, and we need to understand like which is the better solvent. Is the cyclohexane better solvent or the dichloroethane a better solvent? Density of polystyrene, dichloroethane and cyclohexane is given in the question already. So how we can calculate the Fleury-Huggins interaction parameter for polymer solvent system? So solve this question, because already the equation of second viral coefficient is given. A2 equals to d1 upon m1 d2 square 1 by 2 minus chi is given. So chi value we can calculate from this equation, right? Because we have other parameters known. So this is the hint. Now you can solve it, right? So let's see the solution. So in the polystyrene and dichloroethane system, first we are calculating for that, and this is, as we discussed, given. So we can convert the chi equation is equals to half minus A2 m1 d2 square by d1. In this, A2 is given for the dichloroethane, which is as 2.88 into 10 to the power minus 4, right? And then m1 we need to calculate, which is the molar mass of the dichloroethane, and we know the dichloroethane is C2H4Cl2. So 12 into 2 plus 4 into 1 plus 35.5 into 2 is equals to 99 as its molar mass of the dichloroethane, which is N1. D2 is the density of the polystyrene, which is 1.05, and we'll square it and divide by density of the dichloroethane, which is 1.24. So when we put, we get the chi as 0.475, right? Same we will be doing for the polystyrene and the cyclohexane solution, and we know that the cyclohexane formula, chemical formula is C6H12. So 12 into 6 plus 12 into 1, which is giving 84 as its molar mass, and we can put 1 by 2 minus A2, which is for cyclohexane is minus 0.37 into 10 to the power minus 4, multiply by its molar mass, which is 84, and then multiply by the density of the polystyrene, which is 1.05 square, and then divide by the density of the cyclohexane, which is 0.77. So we can get 0.504 as the value of the chi in case of polystyrene cyclohexane system. So we can see that the chi is greater than 0.5 in case of cyclohexane, and it is lesser than 0.5 in case of the dichloroethane. So dichloroethane is a better solvent. So thermodynamically, dichloroethane is thus a better solvent than cyclohexane for dissolving polystyrene. Now let's move to the next question. A polystyrene PS sample was dissolved in benzene to obtain two dilute solutions of different known concentrations. So we have polystyrene in the benzene, and then in the two different concentrations which are generating two different osmotic heads. The measurement of osmotic head, which is nothing but the height difference in the two columns of the osmometer for these solutions at 30° Celsius with a static equilibrium osmometer, produce the following data. So we have this polystyrene into the benzene, and it is having at the two different concentrations, and it is generating two like the osmotic heads with respect to the concentration at 30° Celsius, and we know the density of the benzene and the PS at 30° Celsius as 0.868 and 1 gram per centimeter cube. We can assume that the solution is dilute, and then we can neglect the terms having third viral coefficient and above. Because the solution is dilute, we can neglect it, and G value is given as 9.81 meter per second square, and A is, we need to calculate the number average molar mass of the polystyrene, and these are the four options. We need to see which one is correct out of these four. So how we can calculate? Let's see the solution. So first what we need to do is, we need to calculate the osmotic pressure and divide by the concentration. Osmotic pressure, which is pi, divide by C value. We need to calculate for the one concentration, which is 2.6, and then second for the 7.55. We need to calculate this pi by C, which is osmotic pressure divided by concentration value for two concentrations, right? So how we can do this? Because we know that there is formula which is saying pi by C equals to something is there, they say RT by Mn, RT by Mn, which is the number average molecular weight, plus RT into something, right? which is in terms of the concentration, RT C divide by something. There is some kind of formula, and we need to calculate the number average molecular weight, or the number average molecular mass of the polystyrene we need to calculate, right? We need to calculate number average molecular mass. So for calculating it, we need to have this pi by C, which is the osmotic pressure divided by concentration, so that we can put into this equation and we can calculate. So what we are doing is, first we are calculating pi, which is the osmotic pressure. So convert the osmotic head. We need to convert this osmotic head into the osmotic pressure by the formula pi equals to rho GH, which is, rho is the density of the benzene. So pi equals to rho, which is 8, here it is given as density equals to 0.868 gram per centimeter cube. So we are taking in the meter system, and we can get 868 into the then the rho, then G, which is 9.81, and H, which is 0.14 into 10 to the power minus 2 meter. So we get 11.921 Pascal as pi, which we can divide by the concentration, which is the 2.6, and we can get the value as 4.585 Pascal meter cube per kg, right? We have converted all the systems into the kg meter system. So 2.6 gram per decimeter cube is 2.6 kg per meter cube, right? And in 0.14 centimeter is equals to 0.14 into 10 to the power minus 2 meter. So we have put, and we have calculated pi first. Pi is equal to rho GH, and then we divided by this concentration 1. So we have calculated for concentration 1, we have calculated 1 pi 1 divided by C1. Now similarly we will calculate pi 2 by C2, which is pi 2 is equals to rho, which is the density of the benzene is 0.868 or 868, like in the kg and the meter system we have converted, and then we are taking 9.81 rho G, and then H is height is 0.966 into 10 to the power minus 2 for converting into the meter, and then we get 82.2557 Pascal, and then we can divide osmotic pressure by the concentration 2, which is 7.55. Here it is saying that concentration is 7.55, and we can divide, and we can get 10.895 Pascal meter cube per kg. Now we are having pi 1 by C1 and pi 2 by C2 we are having, right? So we can put, as we discussed, there is one equation which is relating the osmotic pressure to the number average molar mass, which is pi by C equals to RT multiplied by 1 upon Mn plus A2, which is second viral coefficient, multiplied by C, and this is the our equation. So we have in this equation, we can equate it equals to A1 plus A2C. So pi by C is equals to A1 plus A2C, right? We can put, and A1 here is RT by Mn bar, and A2 is RT into A2, which is the second viral coefficient, right? And for one concentration, which is 2.6, we already have pi by C1, which is 4.585 4.585 equals to, we are taking A2 in this, from this like formula we are taking A1 plus A2 into concentration, which is at 1 is 2.6 concentration. So we are getting this equation 1, and then for 2 second concentration, which is 7.55, we are taking pi 2 by C2, which is 10.895, is equal to A2 plus A1 plus A2 into C2, which is 7.55. So we get equation 1 and equation 2. Now equation 2 is minus, like is subtracted with like from the equation 1, and we get 6.31 equals to 4.9582. So from this we can get A2 as 1.275, and when we put in the back into the equation 2, we can get A1 as 1.269. So we know the A1 and A2 value now, and then like we know A1 and A2 value, right? And what we can do is we can just we know that A1 and A2 is equals to, A1 is equals to RT by Mn bar, and A2 is RT into A2, which is second viral coefficient. So for calculating the number average molar mass, we can take A1 is equals to RT by Mn bar, which is equals to A1 value is equals to 1.269, which is 1.27, right? So Mn we can calculate is equals to RT, which is 8.314, into T, which is the temperature 303.15. As we know, the temperature is 30 degrees Celsius here in this case, and we computed it into Kelvin. So 303.15 divided by the A1, which is 1.27, and the value we get of the molar mass of the polystyrene is equals to 1984.56 kg per mole, which is around 2000 kg per mole, right? So what we did is we have converted the we know already the formula of pi by C is equals to RT, this formula RT Mn bar plus RT A2C, we know this. So we know that we can, from this we can calculate the molecular mass, number average molecular mass, right? So we first get the left hand side clear for the 1 concentration 1 pi 1 by C1, and for concentration 2 pi 2 by C2, and we put and we make the linear equation out of these two equation, and we calculated A1 and A2 value, and we know that A1 is equals to RT by Mn bar. So we just put the A1 value from the calculation, and we calculated number average molar mass, which is the option third number 1983 kg per mole. Now the second part is saying to calculate the second viral coefficient, which is A2. So out of these, which should be correct? So we know that A2, small a2, is equals to RT capital A2, right? So we can calculate from this. So A2 is equals to 1.275, and which is equals to RT into A2, which is second viral coefficient. So second viral coefficient is nothing but 1.275 divided by 8.314 multiplied by temperature, which is 30 degrees Celsius or 303.15, and we can calculate that its value is 5 into 10 to the power minus 4 mole meter cube per kg square. So the option second is correct. So are you solving this question and understanding? So let's move on to the next question, which is a polymer solution was cooled slowly until phase separation took place. So a polymeric solution is in like we are cooling it so that the two phase we get. The volume fractions of polymer in the two phases at equilibrium were found to be 0.1, 0.01 and 0.89. So we have the volume fraction of the polymers in the two phases at equilibrium. Now it is saying that using the Fleury-Huggins equation for delta mu1 and the equilibrium condition is delta mu1 dash is equals to delta mu2 double dash. It is saying delta mu1 dash is equals to delta mu2 dash, and we need to obtain a value for chi, which is polymer solvent interaction parameter at the phase separated part. Like one system is in the single phase and it is getting separated into a two phase system, right? So what we need to do is we need to calculate its chi value, right? And it is given that the volume fraction of the polymer at phase separate, like at the equilibrium, the two phases will be 0.01 and 0.89, and we know that delta mu1 equals to delta mu2, right? So how we can calculate? Let's move to the solution. That in order to use the Fleury-Huggins equation for delta mu1, the number average value of sigma, which is the number of the segments per polymer molecule, should be known, right? For calculating delta mu1, we need to know sigma value, but for the most of the polymers, sigma will be sufficiently large. So if sigma is very large, 1 upon infinity will be 0, which will be subtracted by 1 minus 0 equals to 1. So this value will come to equals to 1 for most of the polymers, right? And then from like what we can do, we can just since delta mu1 equals to delta mu2 is there in the equation, so what we can do, we can put this part both side equal. RT will be cancelled from the both part, right? Because RT will cancel with the right left hand side, RT will cancel with the right hand side RT. So ln phi1 plus phi2 1 minus 1 upon this x is nothing but sigma here plus chi phi2 square, right? So we can just equate both of these values. So ln, right, ln 1 minus 0.01, which is we are getting like ln phi1 is there. So we can calculate 1 minus of 0.01 as phi1. So ln 1 minus 0.01 plus phi2, which is 0.01 already given, right, multiply by 1 minus 1 upon sigma, which is nothing but equals to 1 plus chi into phi2 square, which is 0.01 square. So same will do for the mu2, right? ln 1 minus 0.89 plus 1, which is already like 1 minus 1 upon phi 1 upon sigma is equals to 1, multiply by phi2, which is 0.89, and then chi multiply phi2 square, which is 0.89 square. So we can calculate chi as 1.66 from this, right? So you understood the question, the solution part. We just since it's already given that mu1 equals to mu2, so we put this ln phi1 plus phi2 1 minus 1 upon sigma plus chi phi2 square. We just put both side equal and we just calculated chi value from this. since one only is unknown, rest were known. Let's move to this question. Osmotic pressure measurements on a high molecular weight polystyrene sample in cyclohexane at various temperatures yielded the following value for the second viral coefficient, and the temperature is given as 25, 30, 35, 40, and with respect to that A2, which is the second viral coefficients, are given. We need to determine that this polymer solvent system is there, so we need to determine the temperature of the theta condition, theta temperature, and the entropy of the dilution parameter, and the heat of dilution parameter, where the specific volume of the polymer is given and the molar volume of the solvent, which is nothing but the cyclohexane at 27 degrees Celsius, is given. So how we can solve this? We need to first calculate the theta temperature, right? And then entropy of dilution and heat of dilution, and we know all the temperature values, and we know the second viral coefficient values, right? So what we can do is we can first plot in the x-axis we will be having this temperature, and on the y-axis we are having A2, which is second viral coefficient value. So we already know the temperature values in degree Celsius. We can convert it into Kelvin first, right? We will convert it into Kelvin, and when we will take 1 upon T, like 1 upon its Kelvin value of the temperature we will take. So these value will be plotted on the x-axis, and A2 will be plotted as it is on the y-axis. By plotting we get a linear this curve which is having a negative slope, right? So we know that for calculating the theta temperature, we should have A2 equals to 0. Whenever A2 will be 0, that temperature is known as a theta temperature. So A2 is 0 here, and when we will calculate here, we get the some value. So what we will do? We will do the reverse of that value, and then we will take the Kelvin into degree Celsius, back calculation we do, and then we get the 34 degree Celsius as our theta temperature. Now second part is saying to calculate entropy of dilution parameter. So we know already this formula, A2 is equals to entropy of dilution parameter multiplied by 1 minus theta temperature divided by the normal working temperature multiplied by V2 square divided by V1, right? We know this already. So here V2, like what we will do is we can calculate this entropy of dilution parameter is equals to A2, which is second viral coefficient. And how we can calculate the second viral coefficient value? At 27 degrees Celsius we need to calculate. We can convert it into the Kelvin, 300 Kelvin, and we take 1 upon 300, right? We know we can take 1 upon 300, and what we can do is from here we can calculate its value as 0.26, which is somewhere near here, right? So we from this we know the temperature. We can see at this what is the value of A2, which is second viral coefficient, which is nothing but minus 0.26 into 10 to the power minus 4, and then V1, which is the molar volume of the cyclohexane, which is 108.7, and then divide by 1 minus theta temperature, which is 34 degrees Celsius or 307 Kelvin, divide by 30 degrees Celsius or 300 Kelvin, multiply by the specific volume of the polymer, which is 0.96 given in the question, the square, which when we calculate we will get 0.13 as the entropy of dilution parameter, right? Next, C part is saying to calculate heat of dilution parameter at 27 degrees Celsius. So heat of dilution is nothing but equals to theta temperature multiplied by the entropy of dilution parameter divided by T normal temperature, which is equals to, we know that theta temperature 307 Kelvin, theta temperature as 307 Kelvin, which is 34 degrees Celsius, and we know dilution parameter, entropy of dilution parameter is 0.13, and we can divide by the 30 degrees Celsius, which is the working temperature, and we can calculate heat of the dilution parameter as 0.133, right? So you understood this question? It is a very different question, calculating the heat of dilution, entropy of dilution. So do you have any doubt till now? So let's wrap up today's interaction session. So today's topics, what we have discussed is the phase behavior. First we discussed phase behavior, and then the phase diagram and the phase separation of the polymer solutions and blends. So we discussed in the phase diagram what is the stable state, metastable state, and the unstable state, where the systems are in the two-phase system, right? And then we discussed about the thermodynamics of the polymer blends and the block copolymers, which includes the entropy of the mixing and the free energy of the mixing. And then we discussed about the phase behavior of polymer blends and the block copolymers. Means what we discussed is, we discussed about like the different phases when a polymer is in the blended form or in the copolymer form. We discussed that it converts from the sphere to cylinder when we increase the volume fraction of A, and then the gyrates and the lamella we get, and then again if the volume fraction of A will be further increased, the system will go from the lamella to the gyrates and then to the cylinders to the sphere. But then the discontinuous phase will be B and the continuous phase will be A. But at the lower concentration, the discontinuous phase will be A and the continuous phase will be B when volume fraction of A will be lesser. Then we discussed about the osmotic pressure, and the equation which tells the osmotic pressure is Van 't Hoff equation we discussed, and how the polymer solutes they generates osmotic pressure and helps in the generating the osmotic head we discussed, right? After that we discussed about the different polymer molar mass by the membrane osmometry. Or also we discussed about how to calculate the number average molar mass with the help of the when we know the osmotic pressure value, right? We solve one problem, like some problems also. Then in the next class we will be discussing about polymer molar mass by light scattering, frictional properties and viscometry, and then size exclusion chromatography we will discuss, which is GPC, gel chromatography also, right? Then yeah, so this is my YouTube channel link, and where I will be posting the recorded video of today's week 3 lecture. Others lecture are also already uploaded, week 1 and week 2, and then the Google Drive link is there, where I will be uploading my today's presentation or previous presentation, which is week 1 and week 2, already they are there in the Google Drive. And then my email ID is shikha.s.cl@iitg.ac.in. So you can write your queries there. Thank you so much for joining the today's session. Uh, if you have any doubt, you can ask, or now you can leave the meeting. So no doubts. Yeah, so thank you so much. Next, we will be meeting on the next Sunday, 4 to 6, on the same Google Meet link. So for the next, please go through the lecture videos of the week 4. Thank you so much.